What we're doing today is simply studying radiation, and of course, if you've ever been in a place where a radiation alarm has gone off, you will have heard that. Oh my gosh, it's so loud. Oh, it's terrible. So, that kind of thing you want to avoid, being in a place where you hear those kind of alarms. But what we're going to do today is study the different kinds of particles. So you need to stop your recording and copy this stuff down right now. It should be. Okay, the next thing is to get this screen down and make sure you have this copied. Everything in there will be helpful for you in doing the assignment for today. As you look at this particular section right here, you're just seeing the symbols for alpha, beta, and gamma. And I was trying to point out that these two guys right here are particles. Alpha will not go through a piece of paper. It can't penetrate a piece of paper. So it's a pretty big guy because it has 2 protons and 2 neutrons. And that makes it a helium nucleus, where gamma radiation is just pure radiation. It is not a particle. And what we're going to get down below here in the next little section is how we write these particles in a nuclear equation. So you've already written these down, but if you have not, pause your recording now and write them down. So when we balance nuclear equations, we have to look at these numbers right here, the 2. By the way, what is this guy down here? That is not the mass number. What is that? It's protons, which is also the atomic number. Yeah, there we go. And up here is this is what? This is the mass number. In nuclear equations, it works out exactly the same. Except with beta particles, the deal is that beta particles have no mass, so that's going to be a 0 because they're just electrons. Okay? These guys are electrons, and I should have written that in. Well, the electrons, for all intent and purposes, have no mass, which is why but they do have mass, and so we consider them a particle. Where here with the gamma rays, gamma is absolutely no mass. Okay? It's pure energy. But look at this. What is this electron with a positive charge?
Beta particle.
Yeah, that's a beta particle, all right. And it's also called a positron. So you want to be sure you get that stuff down, because that will help you as you balance these equations. Nuclear equations are balanced differently than chemical equations. Got that, Abe? So, the things that we're going to be balancing, instead of coefficients, which would be out here, we're going to be balancing superscripts and subscripts, which seems really weird, but that's how it works. So, once again, this is called an alpha particle, and that's how we would write the symbol for an alpha particle. We can also write it just like this. But if we wrote it like this, we'd have to put the numbers in too. So both of these work. Okay? Yeah, it looks like a fish swimming to the left. Yeah. Okay, here's the way we balance. And this is what I meant when we balance the superscripts and the subscripts. Think of the arrow here as an equal sign. And there's also an equal sign at the bottom. And so that would be down here. And what we're doing is we're seeing that the superscripts balance and the subscripts balance. So, is 234 equal to 234 plus 0? Yeah, okay. It's simple, I know, but a lot of people try to make it complicated, so I'm trying to keep it simple so you don't think it's complicated. So 90, is that equal to 91 minus 1? Yes. Okay, pretty simple, huh? Okay. It's real math as well. Yes, absolutely. Okay, let's look at another one here. Now, is 222 equal to 218 plus 4? Wait. Whoa, what's the problem? We're not that good at math. You don't have to copy it down. You can come back and copy it later if you like for an example. But right now, I just want to query you and make sure you understand how this works. There's an equal sign right here. Okay? So 222, is that equal to 218 plus 4? Yes. Yeah, of course. Is 88 equal to 86 plus 2? Yes. Yes. Okay, so here's the alpha particle being used in a nuclear equation. Here's a beta particle being used in a nuclear equation. And what would we have to do a positron? Positron. If this were a positron instead of a normal beta particle, what would this sign be? It'd be 1. It would be 1 plus. Yeah, 1 plus. I'm sorry, what was the other question? No, I'm just doing, I'm changing this a little bit. And if this were a plus 1, then this guy would have to be 90, wouldn't he? Or 89. Wouldn't he? And then he wouldn't be protactinium anymore. He'd be another element because this is also the atomic number. Right? A beta or an alpha, they're very different. Look at them. If you have a helium nucleus, you know you have an alpha particle. Or if you had written it like this, right? That's the other way to write an alpha particle. Can be this way, or it could be this way. Either one. In both cases, the thing you have to have is the superscript and the subscript, or you can't balance it. Okay. Betas look like this. Beta fish. Okay. Now, as you do this assignment, I would like you to put in the lines that I'm going to put in right now. Okay? So your sheet looks blank like that. I'd like you to put those lines in because you can do all of your little equations right over here. And this helps keep them separated and so you can see what you're doing. And one doesn't get mixed up with the other. It's just a real simple way to do it. Some people find they can't write small enough, and so just use a separate sheet of paper. Don't try and put it on the back. We put our notes on the back, okay? And now I'm going to go through an example of each different problem type. And you're not going to recognize the problem types until you've done a few, but you'll have a chance to see it here. Now, if you look on your sheet, what is in this blank space right now? Oh, no, there's something there. What's there? What is here? A particle. Look on your printed sheet. What is here? A question mark. There we go. Okay, so when you rewrite this, rewrite it without the question mark. Okay, and label it as A. And now you've got 28 over 13 for aluminum and 28 over 14 for silicon. And now here's how you fill it in. 13 is equal to 1 minus, is it not? 1 minus plus 14, yes? And what would the number have to be on the top? Has to be 0 because, yes, you know it's a beta particle, or you could write it as E. Okay? And there you go. That's all there is to it. Now, before you do anything else, before you think you've got it all figured out, because you're going to make a mistake once in a while, just do this. Look over here. So we see that 0 plus 28 is equal to 28, and minus 1 plus 14 is equal to 13. That's how you check your equation when you're done. The negative 1 is going to throw you sometimes, and you'll just go the wrong way when you're trying to figure out the other one. And you'll see what I mean in just a minute. Everybody okay with this one so far? Okay, let's carry on. Another example, you have your question mark in 23A. Your question mark is over here. And so they're asking you to figure out what the element is. Well, it's really no different. 210 is equal to 4 plus a number. If you like, you can just take 210 and subtract 4, and that will give you the number. And that is? You bet. So 206, and we put the 206 up above, and the number on the bottom? 87. Good. So we got the 87 on the bottom. And now, for the mystery guest to figure out who he is, that what you want to do is look in the periodic chart, and you see this 87. That's your atomic number. Who is our guy? Francium. Yes. So we're going to put in Fr, and that's how we identify the element that it turns into. It really is pretty easy. But you have to be careful because it's easy to make a mistake also. So just when you're done, go back before you go on to your next problem and say, is 4 plus 206 equal to 210? And is 2 plus 87 equal to 89? And you're good. Okay, yes, Sean. Sorry, I forgot to put the recording on. Let's just, we're recording now. But what I wanted to do is just go back through this one at a time. Okay, to get the particle, they said that it's going to produce a beta particle, and that's where these numbers are going to come from. Because beta particles always have a 0 mass number and a 1 minus, unless they have a positive charge, in which case they'll call them a positron. But unless they call it a positron, you want to go ahead and call it a regular beta particle. Now, 55 is equal to 0 plus 55, and 23 is equal to minus 1, and then that would have to be a 24. And what happened in class is a person blurted out that it had to be 22, and that's why you want to check afterwards. Once we have this guy, we want to look on the periodic chart and find atomic number 24, and that's how we know that this is chromium. So we see that E and the beta particle dude are exactly the same thing. Okay, you can write them either way. But you need to be familiar with both, because on a test that you take like the final for this class, you might be given a beta particle like this, and then you have to know the numbers and be able to distinguish that that indeed is representing an electron, which is what a beta particle is. Okay, except for the positron, which is positive, and it has no mass, but it has a +1 down here, or a 1 plus. Okay, here's our next problem, and problem type, and I think this is the last problem type, and this is where I'll end the video. But 227, alpha particle. Okay, so an alpha particle is also known as a helium nucleus. So if we put a helium nucleus in there, what's the mass number for helium? 4. Okay, so we got a 4 up here, and yes, it's a 2 down below. And so we got 4 and 2. Now we can figure out what this guy has got to be over here, because it's the helium particle plus whatever this degrades to. So 4, we can take the 4 from 227 and we get what? 223. And then we take the 90 and subtract the 2, and that would be 89. Yeah? 88, right. Like I said, 88. Okay, 88 is our mystery guest. Who is he? Huh? Radium? R-A? Or radon? Radium, R-A. Yeah. Okay, so you just look in the back, inside back cover, and you see 220. Whoa. Ready? Oh yeah, 88. 88. And so this is an isotope of radium that's not the same as what's on the periodic chart, because the periodic chart shows a mass number of 226. And so this guy has 3 protons missing, which makes him unstable, more unstable than he was before. Okay, so that's the degradation of thorium, and this should help you immensely with your homework tonight. What I did next in class is I had students complete these problems, so you can check these problems and see if you got 21A correct, and see if you got 23B correct. Now that was 21B down here, okay? And copy, and here we go. For 23B, I'll get it, okay, there we go. And for 25B, this guy down here, check that out. And then for 27B, you can check that one out. And, oh, we didn't actually do that one. Anyway, that's it. Thanks for watching. Bye-bye. See you there.